Normal strain relates to changes in length. We have material gets longer in tension, generally speaking, and shorter in compression. Put another S in there. So suppose I have a length of material with an initial length. If I apply loads and put this under tension, the material will stretch. And let's call the distance we stretch just this delta. So delta is the cumulative stretching length in the member through the total distance L. We'll then define the normal strain as epsilon here equals this change in length delta over the original length. So we could look at it as L minus L0 over the normalized value of the original length, L0. We call this uniaxial strain, normal strain, uniaxial strain. A couple assumptions go along with this idea. Number one, the bar is prismatic. Means the cross section is the same throughout the length. The material that this is made up of is homogeneous. And the load is through what we call the centroid. Finally, and most important, we're going to assume a very small strain occurs. So very tiny deformations. If this last condition is not present, then the strain is not actually linear. We call this approach Lagrangian strain. It involves the undeformed original length as the normalizing term. So strain equals our L minus an L0 over, and L0 is our normalizing term. We can juxtapose this with Eulerian strain, which uses the final length as a normalizing term. So we have our final length, which actually we're calling L. So Lagrangian strain we use in our classical mechanics when we're dealing with solid objects, and we're looking at strain relative to its original condition, whereas Eulerian strain is used often in fluid dynamics in things like control systems. So another type of strain. So I mentioned here, in order for this analysis to be valid, we need to have the condition where the strains are small. If we derive strains from first principles, we have to take into account strains in all directions as one idea, but we can look at this as a tensor, 3 by 3 tensor, where I varies 1 to 3 and j varies 1 to 3. So if I were to write down the nonlinear, strain tensor, it would take on this form. This is using index notation, which is notation that Newton liked to follow. Our general nonlinear strain tensor looks something like this, specializing this for just the y-axis. That is when I equals, say, 1 and j equals 1. We're heading along the y-axis. Then we will reduce our tensor into this form. So these first two terms are the same thing as the change in length over the original length. But the second term is a higher order term. The second term is a higher order term. It's on order of delta over L0 squared. And the first term reduces down to a delta over L0. So in a small strain situation, we can lose this. And that's how we end up with our relationship. Strain equals delta over our original length. So this delta over our original length is only valid in really small strain situations. So like when you're dealing with loads on very stiff materials like steel or aluminum or other materials like that. Now, on the other hand, when you start dealing with materials like rubber that strain an awful lot due to loads, this sort of analysis is going to break down. Let's look at a quick example. Here we have a force applied to this arm, and it's attached to a cable. So when the arm rotates counterclockwise, it's pinned at A, and if we move through an angle of 0.05 degrees, we want to figure out what the average normal strain is in the wire BD, or just the normal strain in the wire BD. We could break this geometry down as shown here, and we're going to do a real detailed analysis this way. And initially here, we're going to look at this angle alpha, and we see here that alpha is essentially the arc tangent of the 400 millimeters over the 300 millimeters. And that equals 53.13 degrees. So our approach here is really to characterize this triangle here. Because if we do that, we can figure out what our overall length is, and from that we can figure out what the original length of the bar BD is. So when I found alpha here, then I can figure out what this phi angle is, the angle here between these two lines. So that phi angle is going to be, and let's go with a different color, is going to be 90 degrees minus this alpha, which will give us this angle to the line here, and then we'll add 0.05 to it, and this turns out to be 36.92 degrees if you stick in the 53.13 for alpha. So we can use the law of cosines to solve this. That is c squared equals a squared plus b squared minus 2AB cosine of the angle opposite C. So using that and doing some algebra, recognizing that C is LDB prime, then we end up with this expression after we take the square root of both sides. And the angle here is just at 36.92 degrees we found above. So this equals 300.3 millimeters, which is our initial length, or actually the final length. And we can use that to figure out our initial length by subtracting off, well, our change in length by subtracting off the initial length of the cable. So we can find our strain now. And our normal strain then is the elongated length minus our initial length divided by our initial length. So So 300.3491 minus 300 divided by 300 equals 0.0016. Now you should put in units of millimeters per millimeter, even though that is unitless. Another point to make here is you need to be careful about doing calculations like this. It's very easy to lose your precision by estimating or truncating values. So it's best to do the analysis all in one calculation if possible. The other thing to keep in mind is if you're using a calculator and you're using order, calculators usually follow order operations, you got to be careful when you're doing this numerator denominator idea here, and you don't accidentally take 300.349 and subtract off 300 divided by 300. Okay, that's a lot of work just to find the strain in a length of material here that has been deformed a very, very small amount. We really can shortcut this process by just making some quick assumptions. Since our angle that we're rotating here through is really, really small, that means our deformation on the end here is going to be really, really small. So we can just estimate this by calculating the arc length and estimating that the arc length and a straight line, when you're dealing with a small arc length like this and a straight line representation, they're about the same length. And then for really small angles, this is approximately our delta. So our relationship is 400 millimeters for R times theta of 0.05 degrees. But we need to convert that to radians, so we know that 180 degrees per pi radians results in this length. So our normal strain is a change in length over our original length, and this equals, again, 0.0016, and that's millimeters per millimeter. The same as this.